of 1 over root 2x plus 1. Okay, what should we do? We should rewrite this as the integral from 0 to 4 of 2, well, maybe I don't need to rewrite it. Maybe I'll just go right in and do the obvious substitution. I think the obvious substitution is u equals 2x plus 1. And then du would be 2 dx. Okay, and so I need a 2 in here. So I stick in a 2 and I undo the damage. But it is at this moment that I change my integral into an integral of x from an integral of x values into an integral of u values that I have to change my limits of integration as well. So that's u of 0, u of 4, and 2 dx is du, so I get du over root u. Okay, so that's 1/2. When x is 0, u is 1 is another way of thinking about it. When x is 4, u is 9. And so it's sort of just makes sense that this integral is just going to be this integral because it's just a sort of a direct variable substitution. After all, this u substitution is just really just a bookkeeping maneuver to make it easier to undo the chain rule by reducing the cognitive load on myself. Because it's quite easy to antidifferentiate 1 over root u, but it's kind of complicated with all these constants and stuff to antidifferentiate more complicated things. Okay, so just continuing on with the problem, I will rewrite du over root u as u to the negative 1/2, because now it's in a form that makes it easier to antidifferentiate. And, well, now I just apply the FTC. FTC says that the antiderivative of u to the negative 1/2 is just 2 root u. So that's 1/2 times 2 root u, all evaluated at 9 and 1. And that's just right. Okay. Final answer. This is just root u evaluated at 9 and 1. And so this is just 3 minus 1. So the answer to this problem is just 2. Okay. Woo woo. 103. Sort of squeeze in one more problem. 103 is e to the 3 over x squared dx, and this is from 1 to 3. Okay, well, same old, right? I let u be 3 over x. What is du dx? It's going to be, that's 3x to the negative 1, so it's negative 3x to the negative 2, and so what I really have is that du is negative 3 dx over x squared. That's nice because I just have x squared just sitting down there. Only thing missing is a negative 3, so I stick in a negative 3 and undo the damage with a negative 1/3. Which means I have negative 1/3 integral from, but now that's not 1 anymore, because when x is 1, u is 3, and when x is 3, u is 1, of negative 3 e to the 3 over x dx is, so this just becomes e, yeah, this is just e to the u, to u. And notice how our substitution kind of just like reversed the values here now. So there's a 3 down here and there's a 1 up here. That's because 3 over x is a decreasing function, and so, you know, if you plug in a bigger number like 3, you're going to get a smaller output. And so what most people do in this case is they take an extra step and they apply that integration rule and sort of flip it. So really this is 1/3 the integral from 1 to 3 of e to the u du by applying that rule from last week. Okay, finally now we do it. Well, the FTC says that I can compute this integral if I know an antiderivative of e to the u. Well, I do. It's just e to the u. And so this is 3 and 1. So this is 1/3 times e cubed minus e, and that's it. We just stop there with that. Okay, should I check these last couple or just like assume that I'm right? Probably right.
sort of my kind of thing. What? This is not right. 1/3 e cubed minus e. Oh yeah, e cubed minus e, yeah. Okay, good. And 95 is 0. Jerky problem. Okay, what's left? 4 problems to go.
How long is this video? I bet it's like super crazy long. I'm so sad.
Well, 7. Okay. What's 107? Okay, this is just
Another hard problem. Integral from 1 to 2 of x minus 1 root 2 minus x dx. Okay, what should we do? I am just so experienced that I know exactly what to do. I'm going to let u be 2 minus x. And you're just going to see why this is a great idea. Because then du is just negative dx. And so I now gain the ability to, stick in a negative and undo the negative on the outside. And I guess this should sort of belongs still here kind of in the box or something. If u is 2 minus x, then it means that x is 2 minus u. Yeah. And if that's true, then this becomes negative x minus 1 is just 1 minus u. Because, okay, maybe just even write this here. X minus 1, just subtract 1 from both sides, is 1 minus u. In other words, the thing that caused me to think to do this substitution is because I really wanted this to be just like a monomial, essentially. And in fact, I do get root u du here, because du is just negative dx. So sort of this thing in green becomes du. This thing in purple becomes root u. And now I just have to deal with this thing in blue. But once I have a relationship between u and x, then I just have this. This is just u minus 1. And it seems like we've just gone around in a big circle, but no, man, this is better because now I can just distribute this square root through and get something which is just purely algebraic. Okay, before we go any further, what is u of, when x is 1, u is 1, and when x is 2, u is 0. And so this is the integral from 1 to 0, and most people will then just flip it back. So this becomes, the negative goes away, and this becomes the integral from 0 to 1 of u minus 1 root u du. And I hope you see that that just is way easier to deal with, because now this is integral from 0 to 1 of u to the 3/2 minus u to the 1/2. And this we can just anti-differentiate as is. And we get up a power to 5/2, so 2/5 u to the 5/2 minus 2, up to 3/2, so 2/3 u to the 3/2, and then evaluated at 1 and 0. So at 0 it will die, but at 1 it's going to be 2/5 minus 2/3, so that's negative 4/15, I guess, is the answer to this problem. Except I'm off by a math. Why am I off? Oh man, so many little tiny mistakes. This says it's positive 4/15. 1 to 2, x minus 1. I don't see a mistake. Boom, boom. 2/5 u to the 5 halves minus up to 3 halves 2/3. 2/5 minus 2/3 is definitely, I just don't know. But I guess it is going to be positive, so I must be wrong. Alright, somewhere I made a sign error. I don't want to waste your time anymore finding it. U is 2 minus x. Du dx is negative 1. X is 2 minus u. This is all just true, man. This is all just true. Oh my gosh. X minus 1 is 1 minus u. Ha 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 ha. That's wrong. And I am sorry about this. So that's 1 minus u. And so really that's x to the 1 half minus u to the 3 halves. So that's 2/3. It's a riveting video here. And now we're getting closer to the truth. Okay, so minus 2 for me. Okay, 3 problems to go. 111. This is just more. Integral from negative 1 to 2, not even really. This is the integral from negative 1 to 2 of 2 to the x. Okay, I don't even think this belongs in this section really, because I don't think we should do this problem with substitution, although you can. I think the way to do this is just to do it, man. What's the antiderivative of 2 to the x? We should just be able to do that in our heads. It's going to be not quite 2 to the x, it's going to have to be 1 over ln 2 times 2 to the x, because now if you differentiate this, you get 1 over ln 2 times, what's the derivative of 2 to the x? It's ln 2 to the x. So this is just the right answer. And so I claim this is just the way to do this. So we get 1 over ln 2 times 2 squared is 4 minus, and we got to be careful, when you plug negative 1 in here, that's 2 to the negative 1, so that's just 1 half. So I guess this is, whatever that is, 7 halves. So 7 over 2 ln 2 or something like that. I bet the book probably does some fancy thing. I'm not checking myself. But yeah, this is, of course you can, if you so desire, rewrite this as ln of 2 to the 2. So this is 7 over ln 4. That's how the computers want to write it. Okay, 115, 2 more problems. 115, is this just more? I think this is just more. Slightly different problem. They now say, okay, hey, I got a differential equation for you. dy dx is 2x over root 2x minus 1. I think that's the problem. And 2x squared minus 1. And so, also, there are an infinite number, as we know, of functions which have this as their derivative. So we're looking for some function y such that the derivative of y with respect to x is this. There are an infinite number of those, but then specifically requested is the one which goes through the point 5, 4. So in other words, we're being given an initial condition. Okay, so this is really a throwback to like the 5, 1 problems. But now, okay, well anyway, if this is the derivative of the function, then I want to know the antiderivative. And so what I really am going to do now is anti-differentiate 2x over root 2x squared minus 1. And we're going to squeeze this in the space. I'm going to let u be 2x squared minus 1, in which case du is 4x dx. There's already a 2 there, so I need 2 more, and I had a 1 half on the outside. So this becomes 1 half antiderivative du over root u. Okay, so that's 1 half antiderivative u to the negative 1 half, and we know this to be 1 half. This is going to be times, well, okay, this is just silly because I just know this one, but this is just going to be root u plus c. Really this is root 2x squared minus 1 plus c. Okay, and so
I have some curve y equals root 2x squared minus 1 plus c, but with the additional fact that it has to go through 5, 4. So when I plug in 5 for x, I get 50 minus 1 is 49 squared, that is 7. So I get 7 plus c, but I'm supposed to get 4 out of that, and so c must be negative 3. I think I did that right. Therefore, the real answer to this problem is y equals root 2x squared minus 1 minus 3. Cha, cha, cha. And I think that matches the picture that's in the book. It totally does. Okay, last problem, which is something of a challenge, says... Okay, just erase everything. Last problem, something of a challenge, says, here we go, 159a. What is 159? It says, show that the integral from 0 to 1 of x squared times 1 minus x to the 5th is equal to, so we need to sort of prove this like an identity or something, integral from 0 to 1 of x to the 5th times, what is this? Times 1 minus x quantity squared. Okay, this is, to me, not obvious at all why this should be true. I bet there is some kind of deep geometric interpretation of this if I were to graph both of these. But I'm not going to do that. And I'm also not going to explicitly do these integrals, although I suppose I could. Actually, I think if you try to do it, it gets a little ugly, but it's not impossible. Instead, what I'm going to do is I'm going to start, like any identity proving exercise, with the left-hand side or the right-hand side and go the other direction. And so here, okay, because I've done this problem before, I sort of know exactly what to do, which is, hey, I kind of want this to be a single term. And so I'm going to let u be 1 minus x. If u is 1 minus x, then du is negative dx. And, but then also, x is 1 minus u. Okay, so now I'm going to rewrite this integral. And I'm going to rewrite it as, well, the thing that motivated me to do the substitution, well, first I'll stick the negative in and undo the damage with the negative on the outside. So 1 minus x to the 5th, I now rewrite as u to the 5th, du. And then, what is x squared? Well, x is 1 minus u. So this whole thing becomes 1 minus u quantity squared. And there's this negative on the outside, and now I have to change my limits of integration. Well, when x is 0, u is 1, and when x is 1, u is 0. Now we flip this back, and we get that this is the integral from 0 to 1 of 1 minus u squared, u to the 5th du. But then, well, we're just done. Because u is a dummy variable, and in fact, that's just exactly equal to that. So the problem is over. And so proving that these two integrals are equal does not require actually doing the integral at all. It just requires performing a direct integral substitution, and we get that. Okay, good. Keep watching. The last video is going to be about this Riemann sum packet. And I think in that video maybe is the deepest explanation of all about what's really going on with integration by substitution. But I'll now say goodbye.